Riemann Stieltjes Integral introduction part. Let's recall the definition for monotonically increasing function. Now, what do you mean by a monotonic function? The functions are known as monotonic if they are increasing or decreasing in their entire domain. For example, if I say the function e the power x, it is an increasing function. And if I say e the power negative x, it is a decreasing function, right? Now there is another definition. Let alpha is monotonically increasing function. Now, what is monotonically increasing function? Look, monotonically increasing function, for an increasing function in some interval, if derivative of fx is strictly positive for all x belongs to that interval, that means for every value of x, the value of the function with its derivative is strictly positive. It should be. Then f is monotonically increasing or strictly increasing function. Now in this definition, I am taking alpha, that is monotonically increasing function, on closed interval AB, right? Now since the value of alpha at A and the value of alpha at B is finite, can I say that this alpha is bounded in this closed interval? So therefore, alpha is bounded in this closed interval AB. Let's have a partition P which is equal to x0, x1, x2 up to xn of this closed interval AB. Now corresponding to each partition of this closed interval AB, we write delta alpha I is equal to alpha at xi minus alpha at xi minus 1. Simple? Okay. So clearly this delta alpha I is greater than equal to 0. Why? Because alpha is increasing on closed interval AB. We have taken monotonically increasing function on closed interval AB. Alright. The another definition, let f be a function which is real and bounded both, right, on this closed interval AB, and let alpha is monotonically increasing function on closed interval AB. So I'm having two functions. One is f, which is real and bounded function on this closed interval AB, and is alpha, which is monotonically increasing function on closed interval AB. And now we define mi. So mi will be supremum value of fx over closed interval, because we have to talk about each segments. So this is xi minus 1 xi, right, which is actually your supremum of fx, and small mi is infimum of fx over the segment xi minus 1 xi. Then we define, yes, what is UPF alpha? This will be the sum of all those mi's, right? Capital mi's. We have taken in the last video the sum of all capital Mi to be UPF, right? So here I'm having UPF alpha. So this is equal to, this is defined as summation of all those mi, which is multiply with delta alpha I. Here I have to multiply that value mi's with delta alpha i's corresponding, right? And I going from 1 to n. Remember, now we are going to work on the Riemann Stieltjes integral, where I have to consider this alpha to be monotonically increasing function. So we are working on this function now, right? So LPF alpha will be summation I going from 1 to n small mi delta alpha I. Very simple. Okay. So finally we define the upper Riemann integral, the upper integral f d alpha. Here d alpha should be written here. So this is equal to infimum of u p f alpha, and I have to write what is p. P is a partition on closed interval or of closed interval AB. And then what is the lower Riemann integral? This is equal to supremum of LPF alpha, where again P is any partition of closed interval AB. Now what happens if these two upper Riemann integral and lower Riemann integral will be equal? Then we have f to be belonging to this set of Riemann integrals, right? Okay, so if the upper Riemann integral f d alpha is equal to the lower one, this is f d alpha, then we say that f is Riemann integrable with respect to alpha on closed interval AB in the Riemann sense, and we write f belonging to the special R I'm writing, which depends upon alpha on closed interval AB. So where R alpha is a set of all Riemann integrable functions on closed interval AB. Now the common value of these two integrals which are equal, this is denoted by yes, of course, a to b f d alpha. Or sometimes by a to b we can also write it as a to b fx d alpha x. So this is Riemann Stieltjes integral of f with respect to alpha over this closed interval AB. By taking alpha x equal to x, the Riemann integration is seen to be a special case of Riemann Stieltjes integral. Note, the integration from a to b fx d alpha x is same as integration from a to b fy d alpha y. Right? So it is immaterial which letter we use to represent the so-called variable of integration. So the integral depends upon first f, and then depends upon alpha, then the limit points a to b. So it depends upon these four things. And the two symbols, if you see that summation ci, I going from 1 to n, or summation j going from 1 to n, cj, these are same as both what means? Both means c1 plus c2 plus c3 up to cn. Right? So the integral depends upon f, alpha, a and b, but not on the variable of integration, which may as well be omitted. Right? Of course, no harm is done by inserting the variable of integration, and in many cases it is actually convenient to do so, right? Thank you so much.